It's my pleasure to introduce the keynote speaker of the first session, Professor Shahar Maoz. My pronunciation correct? Shahar Maoz?
Yeah.
Great. He's an associate professor at the School of Computer Science in Tel Aviv University, and he has the software modeling laboratory there. And Professor Shahar Maoz's research interest in software engineering, of course, and especially in the use of models and formal methods for software evolution, model inference, testing, and synthesis. And his work has been published in many top software engineering and modeling conferences, such as FSC, ICSI, FM, and so on. And in particular, he's a recipient of an ERC Starting Grant for the development of synthesis technologies for reactive systems software engineers. And actually, today's talk is about this SYNTECH project. So please welcome Professor Shahar Maoz.
Thank you very much for the introduction and the invitation. I am very happy to present today some of the results of my project, SYNTECH, on synthesis technologies for reactive systems software engineers. Before we start, what is reactive synthesis all about? Reactive systems compute by ongoing interaction with their environment. They include sensors that read input from the environment and actuators that hold the state and represent output. When we model behavior of these systems, we consider infinite runs. That is, these systems are not supposed to halt unless someone turns them off. How are these systems typically developed today? The typical development of reactive systems today consists of several phases: formulating the requirements, some formal specifications and models, an implementation, and a lot of testing, and maybe some formal verification. However, despite iterative processes and excellent advances in testing and verification, behavior over time is difficult to implement correctly. At a very high level, both formal verification and testing look like this. We have a tool called a verifier or some test execution mechanism. We give it as input a program or a model representing the implementation and a specification or a set of tests that represent this specification. The verifier runs and answers yes if the model or program satisfies the spec and no otherwise. Test execution runs and answers yes if the program passes the tests and no otherwise. So in both testing and formal verification, we first create a model or a program and then check whether it satisfies the specification or similarly passes the tests. In other words, we describe the what, we describe the how, and we put them one against the other. Synthesis is different. In synthesis, we have a tool called the synthesizer. The input for the synthesizer is just the specification. If possible, the synthesizer outputs a model or an implementation that satisfies the specification. It outputs no if no such model or implementation exists. So in synthesis, there's no upfront investment in building a model or an implementation, which may or may not be correct. In other words, we describe only the what. The how is computed by the synthesizer. So reactive synthesis is an automated procedure to obtain a correct by construction reactive system directly from its temporal specification. The correct by construction promise is attractive, but as you would expect, reactive synthesis is computationally very expensive. Still, recent work demonstrates that it may be applicable to medium-sized systems in certain domains, and this is where our research is set up. In this context, we imagine a world where synthesis is given. The synthesizer is there and is transparent. Just like the compiler today is considered given and correct by almost all software engineers and for almost all purposes. To be careful, I'm not saying we are there in this new world. However, I am saying that this new world where the synthesizer is given, like the compiler is today, is something worth looking at. So we imagine this new world where synthesis is given and ask ourselves, how should software engineering look like in this new world? Which languages will we use? What would be the engineer's tasks? For example, would we still need testing? And more generally, how would the development process look like? These are some of the questions that we would like to find answers for. And the key observation on the way to providing these answers is that in this new world, where synthesis is given, the development process will be specification-centric. The main artifact that the engineer will write, read, analyze, debug, fix, and evolve will be the specification, not the code. We thus envision a paradigm shift from code-centric to specification-centric development. This is the context of the research project I'm presenting here. Following this high-level introduction, let me start with a very, very simple example written in Spectra, our specification language. Consider a traffic light system for 2 lanes that join into one. We have sensors that can detect cars on lanes A and B. That's our environment. We have traffic lights that can be red or green on lanes A and B. That's our system. There are some assumptions we make about the behavior of the environment. For example, that there are initially no cars detected and that there will be infinitely many cars on each lane. Finally, there are some guarantees, of course, we want our traffic lights system to satisfy. The system should never turn both lights green at the same time, and it should guarantee that on each infinite run, car and green light will be true together infinitely many times in each of the 2 lanes. This specification is written in direct correspondence with an assumed guarantee fragment of LTL called GR1. GR1 has a game-based semantics, a game between the system and the environment. It allows specifications that look like this, so-called non-strict realizability formula over environment-controlled and system-controlled variable. It is a single implication between a set of assumptions and a set of guarantees, where both can specify assertions on the initial state, assertions that should hold on all states and transitions, that is, invariants, and assertions called justices that should hold infinitely often in every infinite run. The specification is realizable if and only if there exists a controller such that for any input set by the environment, the controller's output of system variables creates runs that satisfy this formula. To solve GR1 games, there exists an algorithm by Blom, Weizmann, Peterman, Pnueli, and Sahar, which is a symbolic fixed point algorithm whose worst case complexity is quadratic in the state space. Several synthesizers exist for GR1, where the algorithm is implemented using BDDs. For the specification I just showed, the output of synthesis looks like this: a controller, more technically a Mealy machine that is complete for the environment and deterministic for the system. In other words, it considers all possible environment inputs, and for each input sets exactly one output. The controller is correct by construction with regard to the realizability formula. That is, all its infinite runs satisfy the specification. I just note that this concrete representation of the controller is good only for very small toy examples. The actual representation that we use is symbolic, which scales to controllers with thousands of states over tens of variables. So from the output of the realizability checking algorithm, we construct a controller similar to the one I just showed. We have static synthesis where we construct one BDD that represents all the transitions of the controller. And we have in Spectra just-in-time synthesis, which is also symbolic, but a controller is never constructed. Instead, transitions are computed on demand only when they become required during execution. Just-in-time synthesis is unique to Spectra. It significantly reduces synthesis time and it allows much flexibility at runtime. Finally, we wrap the synthesis output with a simple execution API, next state. At each step, we use the API to give the next input, an assignment to all environment variables, and get the next output, an assignment to all system variables. The API is defined at the level of the variables in the specification. That's all. It does not expose the inner representation of the controller, the BDDs, or anything else from the synthesis implementation details. This is something we do in order to make synthesis transparent. One does not have to know anything about BDDs or on how the controller was constructed in order to execute. In the main part of the talk, I will present three aspects of the SYNTECH project: the Spectra specification language, Spectra tools, which is a set of tools and analysis, and example applications developed using the language and the tools. I'll start with the applications. Which systems can we synthesize and execute using reactive synthesis? Over the last 5 years, we have run several elective project classes for third-year CS undergrads. In these semester-long classes, small teams of 2 to 5 students used Spectra to develop and run simple reactive applications, Lego robots, and other simulations. Before I tell you a bit about the applications the students created, let me tell you how we teach Spectra to these undergraduate students. Well, we teach Spectra like we teach Java. Syntax and semantics by example with hands-on practice. Nothing about LTL operators, formal semantics, BDDs, fixed-point algorithms, and so on. This is part of our attempt to make reactive synthesis accessible and useful for software engineers. As I said before, the synthesizer is given, transparent, just like the compiler. You don't need to know how it works in order to use it. The engineers, and in our case, the undergrad students, can focus on the application and the specification. I'll get back to teaching later. So our undergrads developed many Lego robots. A robot that sorts Lego blocks by color, a robotic arm that moves balls of different colors between different bins, an airport shuttle, an elevator, and so on. These robots are small reactive systems. They have sensors like a color sensor, light sensor, touch sensor, and so on. And they have actuators like engines, lights that can be turned on and off, sounds that they can play, and more. I did not want to put here videos on Zoom. It might not really work properly on Zoom, but you are very welcome to find all the specifications and the videos on their website. In addition to these simple robots, some students created simulations of some applications. For example, a smart home system with several rooms, a door lock, and an alarm. The environment detects which person is in which room, and is it daytime or nighttime. The system controls the room lights, the door lock, the camera, and so on. This specification includes, for example, safety guarantees that when there is someone in the bathroom, the light there does not turn off, and that when a baby is in a room alone, the security camera is on. Another example by undergrad students, an airport control tower simulation with planes, runways, buses for passengers, and so on. The environment detects requests for takeoff and landing, weather conditions, and so on. And the system controls access to runways, the tasks for the buses to take and drop passengers, and so on. The specification includes assumptions, such as that it is not always foggy and that requests for departure do not just disappear unless they are granted or some exception happens. The specification includes guarantees, such that when it is foggy or too windy, no requests for takeoff or landing are granted. It includes guarantees about the maximal number of planes that are connected to the terminal at any given time, about not allowing more than one plane to land or take off on the same runway at the same time, and many more guarantees. As another example, a group of students have developed a controller and simulation for a four-way junction with traffic lights, pedestrians, and emergency vehicles. The environment detects cars of different kinds and pedestrians waiting to cross. The system controls the traffic lights. This specification includes safety guarantees that prevent possible accidents and the justice guarantees that make sure no vehicle and no pedestrian will wait for the green light forever. And the last example, a parking lot management system. The environment detects requests for different kinds of cars to enter or exit. The system controls access to the parking spots, opening and closing the gates, and so on. This specification includes safety guarantees, for example, to never let two cars occupy the same parking spot, and justice guarantees, so that when a car is waiting to enter, if there is a free parking spot, it will indeed get permission to enter. All these are examples of specifications and simulations that students develop. Many of these specifications are translated inside the Spectra synthesizer to use more than 40 Boolean variables, some of them more than 70 variables. The specifications that the students wrote typically use more than 10 assumptions and more than 20 guarantees, sometimes many more. They make much use of defines, predicates, enumeration data types, arrays, and some use of patterns, past LTL formulas, monitors, counters, and so on. All of these are different Spectra language constructs that I will touch upon later. Synthesis time for each of these specifications is less than 1 minute on an ordinary laptop, and it is actually typically less than 20 seconds. The synthesized controllers have more than 10K reachable states, but they are described symbolically and never constructed, using our symbolic just-in-time synthesis. All the specifications and simulations are available on the website. And what about the development process of these systems? Note that the systems that the students developed, both the Lego robots and the other simulations, are not large example systems, but they are also not very small or trivial. They interact with their environment in complex ways. So one may ask, how about a more traditional software development process? Implement in some programming language, then formally verify correctness using some formal verification tool. Such a process is of course possible, but it is not trivial. In particular, note that it would still require the students to write a specification to describe the what, just that in addition, they would have to also manually implement the system, that is, to provide the how. I'll be happy to discuss the development process in more detail later. Finally, in addition to the systems developed by the undergrad students, we have used Spectra and Spectra tools to model some classic puzzles as reactive systems. I believe many of you know these puzzles. One nice thing about them is that the problems are known. So when you look at the specification, you can focus on the modeling mechanisms and on the use of the language construct. Another nice thing about these specifications is that they are parametric, and so they allow us to examine scalability. We have created small simulations for these puzzles too, and all are available on the website. All these example applications have been developed using our new specification language and its related toolset. I will now turn to an overview of Spectra. Spectra is built around a simple kernel. The kernel allows one to declare environment-controlled and system-controlled Boolean variables. It then allows one to define assumptions and guarantees of three kinds. Initial assumptions and guarantees on what is expected or should hold in the initial state. Safety assumptions and guarantees on what is expected or should hold on all states and transitions. And justice assumptions and guarantees on what is expected or should hold infinitely many times in each infinite run. The semantics of the kernel, as well as its implementation, is defined by direct translation to GR1 game. However, as I believe you would agree, it is practically impossible to write large and complex specifications, even for example applications like the ones that I have shown earlier, using this kernel alone. So, beyond the kernel, Spectra has language constructs that enable reuse, succinctness, and readability. These include parameterized predicates, enumeration data types, defines, arrays, quantification, bounded integers and arithmetic operations, and also counters. The semantics of each of these constructs is defined by translation to Spectra without the new language construct. Here are some examples. In Spectra, one can declare predicates like the one here at the top, and then instantiate them like we have done here at the bottom. At the top, you see the definition of a predicate named mutual exclusion with 3 Boolean parameters. At the bottom, you see an instantiation of this predicate inside the specification. In Spectra, one can define enumeration data types like we have done here at the top with the data type vehicle. Then we declare 2 variables of type vehicle and can use them in the specification. For example, here, in this guarantee at the bottom, which says that if there is a special vehicle in lane B and no vehicle in lane A, then the system should immediately have green on lane B. In Spectra, one can define expressions like this constant n at the top here, and then use them in the specification. For example, she can declare arrays of size n. Then one can use quantification with for all and exist keywords to succinctly specify properties like this assumption, initially no cars in any lane, and this guarantee. Always, if there is a car only in lane I, then the system should immediately give green light to lane I. These language features help write parametric specifications that are easy to change and maintain. For example, here, if different similar systems have a different number of lanes. Finally, some system requirements involve counting, but it is very difficult to count with the limited constructs in the kernel. In spectra, we treat counting as a separate concern and have a special construct, a counter, that one can declare with a range, an initial value, a Boolean expression that defines when should the counter increase by 1, and with a choice of how to deal with overflows. For example, here I defined a counter to count states where green A holds. I then use this counter in a guarantee that says that maintenance should occur whenever the counter reaches its maximal value. Other counter construct options include a declaration of when should the counter decrease by 1, as well as other overflow approaches in addition to modulo. These include keep, which means to ignore the overflow and keep the current value, and false, which means that overflows are not allowed and are thus impossible. They lead to an immediate violation. Note how the counter construct allows us to encapsulate counting functionality and making it easier to use and reuse. The formal semantics of counters, as well as their implementation, is done by a rather simple reduction to safety assertions. However, the reduction is, of course, hidden from the engineer who writes the specification. In addition to these, Spectra includes language constructs that make it easier to specify more complex temporal properties. These include temporal patterns, past LTL formulas, monitors, and triggers over regular expressions. I will demonstrate two of them here. First, temporal patterns. Previous works have identified temporal patterns that appear in many specifications. However, their semantics is given in LTL, not in GR1. As examples, consider the very well-known response pattern and the P between Q and R pattern that I show here. Spectra includes means to define temporal patterns such as these and use them in specifications for synthesis. We've created a library that covers 52 of the 55 patterns from the well-known list of patterns by Dwyer et al. And additional patterns and pattern libraries can be defined too. The reduction of the patterns to assumptions and guarantees in GR1 is based on two translations, from LTL to a minimal deterministic Buchi automaton, and from the automaton to a GR1 fragment, a new variable that encodes the automaton states, and then new initial, safety, and justice assertions that encode the initial state, the transitions, and the acceptance condition of the automaton. The reduction is fully automated, done offline, not as part of synthesis, and it is done once, such that the result is saved in a pattern library. Importantly, of course, the reduction is transparent to the engineer who writes the specification. As an example, consider the P between Q and R pattern from Dwyer et al. We first build a DBA for it. Then we generate the following spectral pattern definition, specifying the initial state of the automaton, its transitions, and its acceptance condition. So one imports the pattern library to the Spectra document, as we have done here at the top, and then instantiate the patterns as necessary. For example, here we show two instances of two different patterns. The first uses the response pattern to say that whenever a pedestrian presses the button, eventually the system will turn on green for the pedestrian. The second says that between giving green to lane A and giving green to lane B, the system must give green to the pedestrian. These are two examples of using temporal patterns in Spectra. Another example of language construct that makes it easier to specify complex temporal properties is the triggers operator. Triggers is the most commonly used operator of PSAIL, and it is supported by verification tools. Its syntax in Spectra consists of two regular expressions, and its semantics is roughly as follows. A run satisfies the triggers operator if and only if, whenever a prefix of the run satisfies the regular expression on the left, the run starting immediately after that satisfies the expression on the right. Again, in Spectra, we support triggers by reduction to GR1. We make this reduction as efficient as possible using an encoding based on symbolic finite automata. The encoding involves a translation from regular expressions to SFA, determinization, and minimization to ensure that we add only a minimal number of auxiliary variables to the synthesis problem. We do all these operations symbolically and thus rather efficiently. Finally, again, this reduction is completely transparent to the engineer who writes the specification and to anyone who eventually uses the synthesized controller. As an example, one can add the following trigger as a guarantee in our specification. This guarantee requires that whenever the pedestrian holds the button and does not get green for 3 consecutive states, eventually the system will give green to the pedestrian. Again, this is of course a very simple example. One can use much more complex regular expressions in triggers, use many triggers in one specification, and so on. To support the use of the language, we have a set of tools for synthesis and additional analysis. So first, Spectra comes with a synthesizer. The most basic feature of the synthesizer is realizability checking for GR1. That is, checking whether a realizing controller exists. This follows the symbolic fixed point algorithm from the work of Blom, Weizmann, Peterman, Panueli, and Saar, and it is using CUDD as a backend BDD library. Importantly, our implementation uses several performance heuristics at the BDD level and at the fixed point algorithm level, which proved to be very effective in reducing realizability checking time. We reported these heuristics in a recent Acta Informatica paper. After realizability checking, the synthesizer supports several kinds of controller constructions. A concrete one, which is good only for very small toy examples, and a symbolic one, which uses our just-in-time synthesis and allows synthesis to better scale to large controllers. However, a synthesizer that supports realizability checking and controller construction is not enough. To support a specification-centric development process, Spectra provides analysis beyond synthesis itself. These include tools to deal with unrealizability, with non-well separation, and with inherent vacuity. All are motivated by issues that the students who use Spectra encountered as part of their work. I will briefly present each of these with an example. First, unrealizability. Some specifications are unrealizable, which means that there is no controller implementation that can promise that all its runs will satisfy the specification. This problem is not uncommon and is not easy to address. Our experience shows that it happens to anyone, students and experts alike, basically to anyone who tries to write a specification for some non-trivial system. So we have designed and implemented several means to help engineers in dealing with unrealizability. Computing an unrealizable core as a form of fault localization, a locally minimal subset of guarantees sufficient for unrealizability. Computing a counter strategy, which describes how can an environment prevent any controller from satisfying the specification. Computing a symbolic counter strategy we call JVTS. That's a more compact and faster to compute representation of a set of counter strategies. And symbolic repairs, computing assumptions that can be added to the specification and make it realizable. I will demonstrate the first two items here with an example. This example specification is very similar to what we've seen before, but with the following additions. A sensor to detect an ambulance in lane B, an assumption that an ambulance is not constantly detected there, and a guarantee saying that whenever an ambulance is detected, it will immediately get green on lane B. This seemingly simple and benign specification is unfortunately unrealizable. In other words, there is no controller that can realize it. Why? One way to help us out is fault localization, computing a locally minimal subset of guarantees that is sufficient for unrealizability. Looking at this score as computed by Spectra, we see that the specification with only these two guarantees is already unrealizable. Now it is easy to see that if the environment detects an ambulance already at the initial state, immediately the system must violate one of these two guarantees. It must give green and not give green at the same time. So what can we do? Let's see what happens if we add an assumption saying that in the initial state, there is no ambulance detected. Here, I added this assumption. Unfortunately, the revised specification is still unrealizable. So we can compute a new unrealizable core. That's the new unrealizable core as computed by Spectra. Now it is perhaps not as simple as before to understand what is the problem. There are three guarantees, not two, and they are not about the initial state. They combine safety and justice guarantees. So one thing we can do is to ask Spectra to compute a counter strategy. The counter strategy shows how an environment can prevent any controller from satisfying the specification. It is thus deterministic for the environment and complete for the system. I will not go into the details of this specific counter strategy now. I'll just note that it forces the controller to a deadlock where it violates the specification by giving both lanes green at the same state. A different kind of deadlock where it violates the specification by not giving green to a detected ambulance immediately. Or it forces the system to stay in a cycle where the justice guarantee to globally finally have car A and green A together does not hold. At a higher level, all counter strategies for GR1 have the same structure. The environment forces the system to either stay forever in some cycles where at least one justice guarantee does not hold, or to reach a deadlock where any choice of output would violate at least one safety guarantee. On the right, we see such a higher level representation of this counter strategy, including a node representing the cycle where car A and green A are never true together. In more complex cases, there are multiple cycle nodes in this representation, but the structure is always a direct acyclic graph. That's an example of the JVTS I briefly mentioned earlier. Before I move to describe other tools, a bit more about handling unrealizability. To compute a core, which is a locally minimal subset of guarantees that is sufficient for unrealizability, as I showed in the previous examples, we use a variant of delta debugging, specifically tailored for use in GR1. As I said before, core computation can be viewed as a form of fault localization and can assist in debugging the specification. The average core size in the SYNTECH benchmarks, meaning in the specifications written by the students, is 5 guarantees. It is typically about 20% of the total number of guarantees in the specification. 20% out of about 25 guarantees in a specification. I would consider this to be an effective localization. Interestingly, many unrealizable specifications that the students have written have more than one unrealizable core. And the majority actually have 2 unrealizable cores. Some have even more than 10. Also earlier, I mentioned repairing of unrealizable specifications. Others have published work on repairing unrealizability by automatically computing new assumptions that will make the specification realizable. There's also one paper about it in the FormaliSE conference this year by Caveza and his colleagues. We have added symbolic repairs to spectra. Still, there are major challenges to making it useful. The repair is symbolically computed rather fast, and it is correct, but the new assumptions are difficult to understand. You cannot expect an engineer or a student to fix an unrealizable specification by adding assumption that she does not understand. Another problem common to many specifications for synthesis is non-well separation. Some specifications allow the synthesized controller to satisfy the specification by forcing the environment to violate some of the assumptions. Like unrealizability, this problem is not uncommon and is not easy to address. It is hidden because the specification is realizable and the controller is synthesized. However, since the runs of the resulting controller may violate the assumptions, it may not satisfy the guarantees. We knew that non-well separation exists in theory, but we had done nothing about it. Then the undergrad students who developed the robots came to us and told us that the synthesizer has a bug. They told us that it creates a controller that violates the guarantees. That was our motivation to start addressing this problem. And so we have added to spectra the following means to deal with non-well separation: detect it, compute non-well separation core, and compute non-well separation strategy. Let's see an example. Here's another variant of the specification we've seen before with a system controlled variable for maintenance. It includes an assumption that in a maintenance state, the environment will not detect a car in lane A in the next state. It also includes a guarantee to initially not have maintenance. Unfortunately, Spectra tells us that this specification is realizable, but not well separated. In other words, the system can force the environment to violate its assumptions. How? Spectra gives us a non-well separation core, a subset of assumptions that suffices for non-well separation. If we remove the other assumptions, we still get non-well separation. And how can the system force these assumptions to be violated? Well, we look at the non-well separation strategy and we see the system can lock the environment into a cycle where maintenance is always true, and therefore car A is never true, violating the assumption GF car A. As a last example analysis, vacuity. Vacuity is a well-known issue in formal verification. It happens when a model satisfies a specification in a vacuous way. Some elements in the specification play no role in the satisfaction. Inherent vacuity is a property of a specification without the context of a model, which is relevant to our setup of synthesis. Some elements in the specification are logically redundant. Removing them does not affect the semantics. Spectra includes means to detect and deal with inherent vacuity, detect different kinds of vacuity, and compute vacuity cores, which are minimal subsets of elements in the specification that are sufficient reason for the vacuity. Here is an example. We call the specification with the counter I showed earlier. Here's another version of it, identical to the previous one, but with an additional guarantee which states always eventually maintenance. Spectra detects that this last guarantee is vacuous. In other words, it is redundant. Removing it will not change the semantics of the specification. To better understand why it is redundant, we ask Spectra for the vacuity core, and we get the following elements highlighted. We see that this guarantee is redundant because given the definition of the counter, its increment whenever green A is true, the fact that it deals with overflows using a modulo approach, the GF guarantee on car and green A, and the last guarantee that says counter green A equals M cycle implies maintenance. Given all of these, and regardless of the other guarantees, in any correct implementation of the specification, the counter green A will reach its maximal value infinitely often on every run. And so any correct implementation will satisfy GF maintenance on every run. Removing this additional guarantee will not change the semantics of the specification. A few more words about inherent vacuity. As part of the evaluation of our recent work on vacuity, we have found evidence that vacuities, such as the one in this example, are common in Spectra specifications that the students wrote. About 80% of the specifications include at least one vacuity. We found that we are able to effectively detect these vacuous elements. On an ordinary laptop, for almost all of the student specifications, we detect all vacuities of each specification in less than 2 minutes. Finally, we further found that removing vacuous elements may significantly reduce synthesis time. So detecting them is not only a matter of comprehension and quality, but also a matter of performance. You'll find additional details about inherent vacuity in the Spectra in our FSC20 paper to appear soon. All Spectra tools, the synthesizer and the different analyses are packaged with engineer-friendly UI inside Eclipse. This UI includes a rich editor with syntax coloring, auto-completion, and so on, and also standard menus for running the different analyses. The tools have been used by the undergrad students who created the example specifications and applications. So I have some reason to believe that they are indeed accessible to engineers. The source code is available on GitHub, and the package version ready to download and use is available from the SYNTECH website. I really invite you to try it out. Check out the example simulations. I think they provide a nice intro to the project. Before I conclude with future research directions on reactive synthesis for software engineers, a couple of additional topics. GR1 is a fragment of LTL, and it is strictly less expressive than LTL. We chose to use GR1 as the kernel for Spectra because it is rather expressive and because it has a symbolic algorithm for synthesis whose complexity is quadratic in the state space, rather than exponential in the state space as the synthesis is for LTL. That said, we have recently presented GR1 star, which extends GR1 with existential guarantees while keeping GR1's complexity. That is, it is still quadratic in the state space. GR1 is a fragment of CTL star and can express properties that are inexpressible in LTL. We have already extended the Spectra kernel to support it. But what does adding existential guarantees to a specification mean? Tier 1 guarantees, like those of LTL, refer to what should hold in all runs. In GR1 star, one can also specify properties that should hold in some runs. It is thus good for specifying example use cases and exceptional behavior that should always be possible, but not always happen. In their basic form in Spectra, the existential guarantees have a simple syntax, and their semantics is intuitive. In every run, in every state, it specifies that it is always possible that the suffix of the run starting in the state will satisfy the regular expression. Here are two examples. The first guarantee specifies that a use case where the pedestrian gets a green light for 5 consecutive states is always possible. The second guarantee specifies that a use case where maintenance is on and there is a car detected in lane B for 2 consecutive states, after which lane B gets green, is always possible. In this way, GR1 star allows the engineer to translate example use cases and exceptional behaviors into the specification for synthesis. This makes sure that they will indeed be possible, these use cases. That is, that the synthesizer will not suggest an implementation that does not allow them to happen. If the specification is unrealizable, it means that the specified possible behaviors cannot be guaranteed. You can hear more about it in our FM19 paper. I'd be happy to discuss GR1 star further later with anyone who's interested. And a different topic. Earlier, I told you how we teach Spectra to the undergraduate students who take their project classes and develop the robots and the other simulations. I told you that we teach Spectra like we teach Java. Syntax and semantics by example, with hands-on practice, nothing about LTL operators, formal semantics, BDDs, fixed point algorithms, and so on. This is part of our attempt to make reactive synthesis accessible and useful for software engineers. As I said before, the synthesizer is given, transparent, just like the compiler. You don't need to know how it works in order to use it. The engineers, and in our case, the undergrad students, can focus on the application and the specification. Here are some early lessons we have learned. Third-year undergraduate students are able to use Spectra without background in formal methods. The synthesizer is truly transparent. Complete specifications are not easy to understand. They are long and complex. But each guarantee and assumption alone, and many times also small groups of assumptions and guarantees, are typically easy to read and to write. The challenges are more conceptual than technical. The students need to get used to the idea that they should specify the problem and not the solution, the what and not the how. Correspondingly, they need to get used to writing declaratively rather than operationally. Finally, they have to reduce data types with infinite domains into discrete and finite ones. It takes a few weeks and exercises, and then at least some students begin to appreciate and enjoy the use of Spectra. Thus, we still have a long way to learn what are the characteristics of high quality specifications for synthesis, what is the best process to use in order to produce such specifications, and how should we teach students write better specifications for synthesis. Finally, a bit more about future research directions. First, it is tempting to add more language features and more analysis. Of course, we have many ideas about that. But maybe before that, or in parallel at least, I think more experience is needed in order to prioritize possible extensions. Which language features are used and how? Are the tools effective? Are the patterns useful? Are cores and counter strategies helpful? We are very much looking for users and collaborators to advance Spectra with us, perhaps help us answer these questions. On the application domains front, we have made an early design decision to define and develop Spectra and the tools as domain agnostic. Still, it is clear that domain-specific example applications put the language and tools into a test and help us move forward. To this end, we've started collaboration with industrial partners in the field of robotic mission orchestration. but this is just one beginning. We're looking for users and collaborators to try out our tools on the application domains of their interest, perhaps running some case studies together. Finally, we suggest a shift in reactive synthesis focus from the synthesis algorithm, from the research on the synthesis algorithms, which have been studied a lot, to the actual execution and use of the synthesized controller. After all, beyond theoretical curiosity, the execution of the correct by construction controller is the real reason why we're interested in reactive synthesis in the first place. A correct controller that will not be executed is not very useful. So in this new focus on the last mile in the reactive synthesis pipeline or toolchain, here are some directions. First, testing of the synthesized controller. Although we trust the correctness of the synthesizer, the controller may still have defects. Why? Perhaps the specification does not correctly express the intentions of the engineer who wrote it. Perhaps the engineer does not know or understand the real environment in which the system would run. We thus need effective means to test correct by construction controllers. The challenge includes means to adapt existing test design and automation techniques, for example, combinatorial test design and scenario-based testing, to the special setup of the synthesized reactive controller. Second, the controller needs to actually run within some environment, which may be very different than the design time environment where the synthesizer runs. For example, a much weaker machine with limited resources. We need to develop new methods for the efficient and flexible execution of synthesized controller. All the results I've presented today are described in these papers and in some others. I'm happy to discuss any of them in detail. With that, I want to thank the super strong students and postdocs I've had the opportunity to supervise and to collaborate with at Tel Aviv University. All the results I've shown are due to their talent and hard work. This completes my talk about the specification language, the tools, the example applications, and the future research on reactive synthesis for software engineers. Thank you very much for listening.
Thanks so much for a great talk. And it's quite impressive about this nice spectra tool. There's some question in the Keynote channel. So it's a question from Ronggu. And his question is about the relationship between synthesis and verification. So some example is that if someone uses model checking to generate a counterexample or witness of reachability, then does it mean that the result of synthesis is obtained using model checking?
Okay, so yes, in some sense, the counterexample generated by a model checker is, I would say, a very small example of synthesis. Yes, but in the context of the project that I described, synthesis is the main thing. It takes as input the entire specification, not just a single assertion that you want to check. And so it's not limited to fixing some bug, but to generate the entire controller, the entire implementation from scratch.
Okay, the second question is from David from Imperial College. Is about counting unrealizable cores. So do you need to traverse all subset of guarantees, or delta debugging helps to find one core efficiently? But what about counting all cores? Can this be done efficiently? That's a question.
That's a great question, because yeah, we have work in progress that I didn't show about computing cores. So unrealizability is monotonic, which means that using delta debugging. It's the computation is only quadratic in the number of guarantees to find a single core. Then, yes, in the worst case, you have to check all subsets. So an exponential number of subsets of guarantees. But we do have heuristics that is not yet published on how to do this rather fast in many cases, relying mainly on the monotonicity of unrealizability.
Great. So next question is Gareth from Siemens. What, in your opinion, is the biggest obstacle for industrial adoption of your tool or technique?
Okay, well, there are, I would say, there are obstacles in several dimensions. On the expressive power dimension and complexity, you can see that we model systems that are discrete. They have large state space, but finite, but the variables are defined over finite domains. Everything is discrete. There's no real time. So in a sense, at least for now, this limits applicability to many systems. I'm aware of it. Also, we have not yet included in Spectra anything about uncertainty and probabilities. Maybe that's a good next step to do, but we haven't done that yet. That's on the expressiveness of the language and the controllers. There is also another, on the other dimension, there is, I think, a barrier in terms of development process, the conceptual development barrier to change the development process, to not implement and check, but to start with a specification and working on it. I think that's another barrier.
Okay, thank you. So probably this is the last question. So because of the lack of time, so you can feel free to use this Slack channel to ask additional questions after this talk. So the last question for this live session is Matthias from Hamburg University. And I wonder whether it is possible to export the normalized model from Spectra. Is that, I mean, a model purely in the GR1 kernel without any predicates, patterns, and so on. So Spectra is great and supported for syntactic elements, but they are a bit problematic when one wants to use Spectra models in other tools. So that's a bit.
Okay, so yes, we actually have an interface to use the input language of another synthesizer called slugs on Spectra. So Spectra accepts slugs input too, and yeah, that's what we have currently. If there is a specific format that somebody wants to use, perhaps we can help.
All right, so great. So thank you again for nice talk and also accepting this great invite talk in these difficult times. So thank you again, Professor Shahar Maoz.
Thank you very much for listening.